The following is a selected video from masterthecontent.com, where you will find an extensive video library of lectures for a variety of standardized admission tests. We offer over 600 hours of detailed video lectures for a multitude of standardized tests. Use our interactive in-lecture table of contents to find specific topics of interest. Work through numerous in-lecture examples to help you internalize concepts. To learn more, visit masterthecontent.com. Your career, our passion.
Ionization energy. Let's begin by taking a look down here at figure 1.8. Now, if we add energy, right? So if we add energy to an atom, as we see here, then we can make an electron jump to a higher energy level, right? We can get an electron to jump to a higher energy level. Now, if that electron gains enough energy, it can actually be removed. It can be removed from the atom. And once that electron is removed from the atom, we're left with an ion. And it's an ion because it has lost an electron. Now, the amount of energy that it took to actually remove this electron, that energy is what is known as the ionization energy. So let's go ahead now and read our definition. The ionization energy is the amount of energy needed to remove the highest energy electron from a gaseous atom or ion, and the units for ionization energy are kilojoules per mole, as we see here. Now, more than one electron can be removed from an atom, and it will take place sequentially. If we take a look over here, we see that there's an initial amount of energy that was required, and then we're left with a monovalent positive ion, as we see here. Now, again, with energy, we can remove another electron, and then we're left with a dipositive ion, and then with energy again, we see that with this reaction, a electron is removed again. Now, one other thing that we should note is the amount of energy required to remove that first electron, right? That's known as your first ionization energy, right? So that's going to be the energy required to remove one electron. Now, the amount of energy required to remove that second electron, that's known as your second ionization energy, and so on for the third ionization energy. And furthermore, the second ionization energy is always going to be higher than the first ionization energy because it's harder to remove that second electron. And we'll discuss why in just a few slides. Now, next, what we should do is let's go ahead and point out the ionization trends and examine them on the periodic table and explain as to why they exist as they do. Now, looking here at figure 1.9, we see that the ionization energy trend increases going from the left to the right on the periodic table. Furthermore, it increases up a group, right? As we see here as well, the ionization energy. Now, let's go ahead and explain this trend first as to why it increases across a period. Then we can take a look at why it increases as we go up a group. Now, if you recall in part 1b of this lecture series, right, on this slide here, we had demonstrated that group 1 elements have one valence electron, right? They have one valence electron. So we'll pick up from that thought. And if we come back here, we see that group 1 elements have one valence electron. Now, to obtain a full outermost shell, they would rather give up that one electron than gain electrons. Thus, on the left side of the periodic table, we could generalize that we're gonna see that these elements here, they're gonna give up their electrons rather than gain electrons. Now, if we contrast that with, for example, the halogens, that being main group 7, right? They have 7 valence electrons, right? They have 7 valence electrons, and they would rather gain 1 electron than give up 7 electrons to obtain a full most outer shell. Thus, as we see here, the right side of the periodic table would rather gain electrons, while the left side of the periodic table would rather give up electrons, right? So then it makes sense that the ionization trend increases going to the right because it's going to take less energy to remove those valence electrons on the left side, and it's going to take more energy to remove those valence electrons on the right side because, as you see here, they would rather gain electrons than give them up. Now, how about as we move up a group? What's taking place there? Well, as we move, if we take a look at group 1, so we'll take a look here at group 1. As we move, if we take a look at the valence electrons in group 1, as we're moving down the row, we're seeing that those valence electrons, they're going to be on subsequent quantum levels, right? They're going to be on subsequent quantum levels, those valence electrons. And if they're going to be on subsequent quantum levels, then what's going to end up occurring is those valence electrons are going to be farther from the nucleus. And if they're farther from the nucleus, they're not going to have an attraction for the nucleus that is as strong. And that term that we had used in part 1b, that was called the effective nuclear charge. Thus, as we move down a group, right, the valence electrons are going to have a smaller effective nuclear charge. Thus, these electrons are going to be easier to remove, right? They're not going to require as much energy. Thus, they have a lower ionization energy. Now, as we move up a group, those valence electrons are going to be closer to the nucleus, and they're going to require more energy, thus a higher ionization energy to remove them from the atom. Okay, great. Let's delve a little bit deeper now and take a look at figure 1.10. Excuse me, for a second, let's come back up here. So on the previous slide, we had just stated that the ionization energy increases to the right going across a row. One irregularity in that trend we can actually see